Hey, welcome to The Explainer. Today, we're going to pull back the curtain on something that might sound a little technical, but I promise you it's the unsung hero that basically unlocked the entire deep learning revolution. We're talking about batch normalization.
So have you ever wondered why AI models suddenly just got so deep so fast? For the longest time, there was this invisible wall. We just couldn't build truly massive neural networks. Why? Because the deeper you went, the more they just descended into total chaos. They became impossible to train. And this wasn't just, a small bug. This instability, this chaos, it was a fundamental roadblock. It made training these deep networks this incredibly slow, super frustrating, and a lot of the time, just a flat-out impossible task. It was holding back the entire field of AI.
All right, let's get into the weeds a bit. To really get why batch normalization was such a big deal, we need to understand the problems it was built to solve. And there were really three major headaches.
Okay, first up, we've got a term that sounds way more complicated than it is. Internal covariate shift. Just think about it like an assembly line, right? Station 1 makes a small change. Well, now the parts it sends to Station 2 are different. So Station 2 has to recalibrate, but that changes what it sends to Station 3. It's this chaotic domino effect, and that's exactly what was happening inside these deep networks. Every single layer was trying to learn, but the data it was getting from the layer before it was constantly changing. It was like trying to hit a moving target.
Problem number 2 was all about bad communication. See, for a network to learn, the layers have to send signals backward to each other, but these signals were going haywire. Sometimes they'd shrink down to basically nothing, that's the vanishing gradient, or they'd blow up and get huge, the exploding gradient. It's like the layers were either whispering so quietly that nobody could hear them, or they were screaming so loud that it was just noise. Either way, no real learning could happen.
So you put all that together and you get this trifecta of trouble. Training took forever, getting these networks to work at all was a nightmare, and they were so sensitive to how you set them up. I mean, if you didn't get the initial settings just right, the whole thing was basically doomed from the start. This was the wall that deep learning had hit hard. But then 2015 rolls around, and a paper drops from Sergei Iyov and Christian Szegedy. They introduced a new technique, and honestly, it changed everything. It was this stunningly simple idea that just brought order to all that chaos. So here's the core idea. It's brilliant. What if you could just force the information being passed from one layer to the next to always look the same, to have a consistent, predictable shape? That's what batch normalization does. It's like putting a little quality control manager at every single station on our assembly line, making sure every layer gets perfectly standardized parts to work with every single time.
Okay, so how does this magic quality control actually work under the hood? Well, it's actually a pretty straightforward, but really powerful three-step process that basically stabilizes the whole network from the inside.
It's actually beautifully simple. So, step 1. For any little batch of data that comes through, the layer just calculates the average value and how spread out the data is. Step 2, it uses those numbers to normalize the data. It basically recenters it to have a mean of 0 and a variance of 1. But here's the really clever part. Step 3. To make sure we're not crippling the network, it adds 2 little knobs the network can learn to turn. One to scale the data back up or down, and another to shift it. This gives control back to the network, so it can find the best possible data distribution, but it's always starting from that clean, stable, normalized place.
And the effect of this was huge. By putting this simple little quality control check at every single layer, the entire way we train these models was just revolutionized. All of a sudden, a whole new world of possibilities just opened right up.
You can really see the domino effect here. Once you had stability, everything else fell into place. Training got way faster. The little bit of randomness from using batches actually helped the model perform better on new data. It was like a free bonus. That nightmare of picking the perfect starting point, mostly gone. Those pesky gradient problems, tamed. And the big one, researchers could finally build and train the ridiculously deep networks they had always wanted to.
And the speed increase was just wow.
Because the whole system was so much more stable, you could crank up the learning rate, like how fast the model learns. We're talking sometimes more than 10 times higher than before, without everything just exploding. That meant models could be trained in a tiny fraction of the time it used to take.
And look, this wasn't just some abstract idea in a research paper. No way. Batch normalization almost overnight became a core building block in the deep learning world. Let's take a look at where it really showed up.
So, if you've ever heard of those legendary models like ResNet or Inception, the ones that completely changed the game for computer vision, well, you've seen Batch Norm in action. Those models have hundreds of layers. Hundreds! They would have been literally untrainable without the stability that Batch Norm gave them. It was the key that unlocked the whole thing.
You know, the idea was so good that it spawned a whole family of different types of normalization. So you have batch norm, which is still the king for most image stuff. But then you have layer norm, which became essential for transformers and all the big language models. And then there's instance norm, which found its home in creative AI, like style transfer. They all work a little differently, but they're all based on that same brilliant core idea: enforce stability.
And really, that just gets to the heart of it all. This quote from the original paper says it perfectly. What made batch normalization so powerful wasn't that it was this super complex, hard-to-understand thing. It was the opposite. It was a simple, elegant fix for a huge fundamental problem. And the best part? It just worked.
So, what's the big takeaway here? I think it's that sometimes the biggest breakthroughs don't come from adding more complexity. They come from finding clever, simple ways to create stability. Batch normalization tamed that internal chaos and let AI models grow deep. And that kind of leaves us with a huge question, right? As today's models get bigger and bigger, what new kind of chaos is hiding inside them, and what's going to be the next beautifully simple idea that comes along to tame